All right, hi everyone. Welcome back to section 7.3 and continuing on our content for section 7.3, we're going to be taking a look at our second translation for Laplace transforms, and that's going to be translation over now the t-axis. Okay, so how does this essentially work? So differential equations, we're going to tie it in a little bit to engineering. And in engineering, we encounter functions frequently that are either on or off functions. Think about turning a faucet on, turning a faucet off. Okay. So, some more examples in a less simplistic form is an external force acting on a mechanical system, a voltage impressed on a circuit that can be turned off after a period of time. So, if that's the case with these real life applications, it is then very convenient to define a very special function that is zero, meaning off, up until a certain time t equals a, and then the number one on after that specific time. Okay, so this type of function that's zero and then one on and off is a type of function called a unit step function, or also known as the Heaviside function, which is a very cool name. So definition of a unit step function. Okay, so the unit step function, it looks like this. U of t minus a is defined to be this piecewise setup right here, on and off, 0 and 1. So 0 from the piecewise is 0 from 0 to 0 to a, and 1 when we're greater than a. So that is the unit step function. Okay, it's u of t minus a, and it's a piecewise setup, turning a function off and then on. So how does this essentially work? Okay, so when a function f of t is defined for t greater than 0 and is multiplied or multiplying the function f of t by a unit step function, what the unit step function does, think about it as like a device, as a tool. What it does is turns off that function or it turns off that function for a portion of the graph. So let's look at it right here. So in this figure, the unit step function turns this function off up until a, and it turns it on after a. So this is the function f of t times u of t minus a. It turns the function f of t off and on, which is pretty interesting that we have this specific tool in mathematics. Okay, so a couple more things since we're dealing with these unit step functions is they dive into piecewise functions. So one of the key things about Laplace transforms is they need to be piecewise continuous functions. So we're kind of going back into this criteria here. So general piecewise functions, a unit step function can also be used to write a piecewise defined function in compact form. A general piecewise defined function of this type, f of t, equals g of t for 0 between 0 and a, and h of t for t greater than a. We can write this as a compact form. So this is piecewise and this is compact. We can write this as a compact form. It could be f of t equals g of t minus g of t times that unit step function, u of t minus a, plus h of t times the unit step function u of t minus a. So we're utilizing that unit step function to take a piecewise defined function and compacting it. And we can even do that with a more specific piecewise function like we have here, where there's three pieces, but two of them are zero. But we could compact that into this formula right here. F of t equals g of t times the unit step function u of t minus a minus u of t minus b. So this is involving another component b. So this is piecewise, and this is compact. A little more specific than the previous general piecewise, but still another form. So let's go ahead and try out a quick example. Example 5, a piecewise defined function. So we want to express f of t equals the piecewise function 20t. That's defined over 0 to 5, and then 0, t greater than or equal to 5. So we're going to use the formulas from the previous page to write this in terms of a unit step function. So, u of t minus a. All right, so let's go ahead and pick out a couple things. So this looks a lot like this general piecewise setup right here. Okay, so we're going to use this. Okay, so we can even rewrite it down here below. Recall f of t equals the piecewise function g of t defined from 0 less than t less than a and h of t for t greater than a. And what does it turn into? Turns into f of t equals g of t minus g of t times the unit step function t minus a plus h of t times the unit step function t minus a. So let's identify a couple things. So we have, I'm just going to rewrite it down here, maybe in a different color. So we have f of t equals 20t, 0, t greater than 5. So let's pick apart a couple of things. So 20 is essentially g of t. 0 is essentially h of t. And 5 is our a. So therefore, writing this in compact form with the unit step function, what we get is 20t minus 20t times the unit step function t minus 5 plus h of t, which is 0 times the unit step function of t minus 5, but 0 times anything is just going to be 0. So that unit step function would just be turning 0 on and off, but that would just be 0 anyways. So what we get is f of t equals 20t minus 20t times the unit step function of t minus 5. And we could even clean it up a little more by factoring out that 20t. So this could be like 1 minus the unit step function of t minus 5. Okay, so that's a little bit of practice of using the unit step function, writing a piecewise function in a compact form. And that helps us out with Laplace transforms because it makes the Laplace transform a bit simpler to work with. But just a little bit of introduction for the unit step function and compacting it. We'll get into Laplace's in the next coming videos. But thank you for watching, and I'll see you in the next one. Take care.